Hello, Mr. Cohan. Hello, Mr. Wilson. My name is Jefferson Torres. This is the solution presentation video. I have chosen the same book as we used, the Calculus for Engineers made by Briggs, the chapter point 7.3, Calculus with Trigonometries. I have chosen the exercise number 71, which is in the page number 522. So let's get started. Okay, so to begin with the explanation, it says prove the following orthogonality relations, which are used to generate Fourier series. Assumed that m and n are integers when m is not equal to n. So in this problem, what we need to show is we need to make a proof. We need to demonstrate that the left hand side is the same as the right hand side. So as you see here, the left hand side is this part of the integral, while meanwhile the right hand side is 0. So we have chosen the left hand side to develop our exercise. First, we begin with integration by parts. This is the theory, and we choose first the sign of mx as the derivative. Then we find the original function. We do the same proceeding, but vice versa. We start with the original function and then with the derivative. So we applied, and then we know that the integration by parts shows that we need to multiply f multiplied by g minus our new integral, which is the f, the function, multiplied by the derivative of g, which is ubicated over here. Okay. And then, as we have another integral here, and we have some constant terms here, the same as this is a definite integral, we conserve the both boundaries to operate later on. Then we decided to make a game because we obtained another integral with trigonometric functions. So in this case, we have chosen the cosine of nx as the function in derivative, and then we change this to the original function. We do the same proceeding for the second one, but in this case, the first one will be g, which is equal to cosine of mx, so the derivative will be minus m sine of mx. So yeah, so as our right hand side is equal to 0, then we can say that the left hand side will be equal to our new left hand side. So the original one will be ubicated in the left part. On the other hand, on the right hand side, we will have our new integral, which is made by the integration by parts. So hopefully you will see. Okay. So here, as you see, we continue operating. We have the sine of mx multiplied by sine of nx, and then this is equal to our new integral, which is the numbers, which is the constant numbers, multiplied by our new integral. But when we take out the constant terms, we notice that we already have one new integral, which is the same as our original one. So then we can apply this method, the bootstrapping method. So the bootstrapping method allows us to take these two integrals to one side and divide it constant terms, as doing like the distributive law, to obtain the answer. So we do the same proceedings, we conserve the boundaries, and then at the end we operate them. We replace them instead of x. So here we have a cosine of pi multiplied by sine of pi. So sine of pi is equal to 0, so these terms cancel, and we have the same case for every term. Then we obtain the original integral, as the original integral was equal to our new integral with the bootstrapping and the integration parts methods. So then we find that our integral is equal to 0. So then, therefore, we know that the left-hand side is equal to the right-hand side. And we conclude that the integral between 0 to pi of the function sine of mx multiplied by sine of nx is equal to 0. Okay, this is a brief side of the proceedings, and this is our answer. Then we have this. We have the part number b, the literal b, which is we need to do the same proceedings. We need to use the bootstrapping method and the integration by parts. So we have our new integral between 0 and pi of cosine of mx multiplied by nx of dx. So we apply the integration by parts method in the same way. So we choose that our first function in if its derivative will be equal to cosine of mx, and the other one will be expressed in the original function. So then we know the rule for the integration by parts. So we replace this information, but we keep working just with the left-hand side. So the left-hand side, our original function is equal to, it needs to be equal to 0. So we just add it up to the first part, the left-hand side, to our new integral, which was made by the integration by parts. So we keep working here. We conserve the boundaries. We take out the constants. And then we ended up with another integral of trigonometric functions. It's not the same as the original one, but it's pretty close. So we apply the bootstrapping method, which I find that it's really useful. It helps me a lot in the assignments. So then we choose the first part of the function as the one expressed as its derivative. Then, therefore, the another one will be equal to the second one, but it will be expressed as the original. So we need to take the derivative for the second one, and for the first one, we just need to find the original one because we have already gotten the derivative function. So okay, so the left hand side, which is the original, is equal to our new integral. Then we take out the constants as you see here, and then in this step we are able to apply the bootstrapping method. So we put our integrals to the left hand side, and then we apply the distributive law, and so we take the constants to the other side as they are multiplying to our integral, so then they will be multiplying our to our other numbers. So if they will be constants, we need to have a condition here. We know we replace here the boundaries, the pi and the number 0, and then we obtain that in each one of the terms there is a sign, so the sign of 0 and the sign of pi will be equal to 0. That's why our numerator is equal to 0. Then here we have another condition. So here in this step we are aware that our function will be equal to 0 because it has been developed as just one fractional number, where n it's equal to any number except 0. So this is a condition that we need to to put here. So end cannot be equal to 0. It can be equal whatever number we need, whatever number we have, but not 0. Otherwise, we will have an indeterminate form. So then, therefore, we demonstrate that the left-hand side of our function, the original one that we took, it's equal to 0. So to conclude this, we just take the left-hand side, we add it up to the new integral, which was obtained by the integration by parts and the bootstrapping method, and then we demonstrate that the left-hand side is equal to 0 to the right-hand side. Okay, so let's move on to the third one, which is the number c. So the number c is the same. It says the integral between 0 to pi of our function. We apply the integration by parts. We choose one of the functions to be the derivative. Another one will be the function g. And then we have these coefficients and the constant. So here we develop the same function. We keep the boundaries. We keep doing the same proceedings. As you see here, we forgot here the line. Then we apply the bootstrapping method. So we put the integrals on one side before we apply the integration by parts. Then we apply the bootstrapping method. We take the constant to the other side. They are multiplying here, so they need to divide in the other side. And we ended up with a number which is 0 over 1 plus n over m. So we need to make an assumption here as the last exercise. So we need to assume that n multiplied by m or divided by m cannot be equal to minus 1. So then we demonstrate that the left-hand side it's equal to 0. Therefore, the left-hand side, which was reduced to 0 by the bootstrapping method, the same as the other exercises, and the integration by parts, will be equal to 0. So this is a brief explanation of our work. We need to make some assumptions. We need to limit in the number b and number c exercises. We need to say that n over b over m cannot be equal to minus 1. So there are some restrictions that are applied, but they are just for the constant, not for the independent variable. Okay, so thank you very much for watching the video, and I hope you like it. And if you have any questions or any concerns, please let me know. Have a good weekend.